So in 4.2, we will continue the discussion of probabilities, and we'll learn a few more tricks to solving these sorts of problems. So let's look at number 11. When randomly selecting adults, let M denote the event of randomly selecting a male, and let B denote the event of randomly selecting someone with blue eyes. What does P, M / B represent? So let's just look at the answer and then we can talk about it. So the answer is B, the probability of getting a male given that someone with blue eyes has been selected. So when we have something like, let me make this generic, the probability of A vertical line B is the probability of A given, so this vertical line stands for given that B happened or occurred. So it's the probability of A given that something else already happened or occurred. Okay, then it asks, so this is the probability of someone being male given that they have blue eyes. Is that the same as the probability of someone who has blue eyes given that they're male? Well, let's think about this. The probability of someone being male given that they have blue eyes. Now, since male and females are pretty much 50-50, so I would wager to bet that even all the blue-eyed people in the world, you could probably split them into two groups, blue-eyed males, blue-eyed females, and I would bet that those two groups would be about the same size, which means this is probably about 50%. Now we ask, well, what's the probability of blue eyes given that they're male? Well, now you have to look at all the men, figure out all the different eye colors. Does this make sense? Count up how many of those men have blue eyes, how many have green, brown, etc. I don't know offhand what the probability of blue eye, well, I could probably say most people have brown eyes. So the probability of a blue-eyed male, it's probably like 30% or something different is my point. Smaller, most likely. So it's unlikely that these two numbers would be the same. Now, it could be the same, but very rare. So generally speaking, we're going to say the probability of A given B is not the same as the probability of B given A. Again, they might be equal, but unlikely for it to be so. So this would be B again. No, because the probability of someone having blue eyes given that they're male represents the probability of getting someone with blue eyes given that a male has been selected. Okay. Oh, I should also mention this is called a conditional probability. So some condition has already been met, and then we look at the probability of something else tied to that condition. Okay, the next one, 12. A research center polls show that 84% of people believe that it is morally wrong to not report all income on tax returns. What is the probability that someone does not have this belief? So let's use W as our event. So W is they believe that it's wrong not to report all your income. Therefore, W bar or W complement would be the people who think that it's not wrong. So we already know from yesterday, I kind of already gave us this because it just felt natural to do so. The probability of someone thinking it's wrong is 84%, so it's just 0.84. What would be the probability of people who think it's not wrong? Or excuse me, yeah, not wrong. Well, we know from yesterday that these two things have to add up to 100%, right? So we know P of W plus P of W complement must equal 1. Therefore, P of W complement is just 1 minus P of W. And I mean, I'm showing you the long way just so we can see the math, but you already know it's 0.16, right? You would have gotten there faster than I could write it down. How? Because you know 84% and 16%, they have to add up to 1. So the probability that someone doesn't think it's wrong is 0.16. Okay. 13 is very similar. So when a man observed a sobriety checkpoint conducted by a police department, he saw 661 drivers were screened and 3 were arrested for driving while intoxicated. Based on those results, we can estimate that P of W equals 0.00454, where W denotes the event of screening a driver and getting someone who is intoxicated. What does P of W complement denote, and what is its value? So W is the person's intoxicated. So W complement is basically just adding the word not. If you've noticed in every one of these examples I've done, all I've done is added the word not or no. So it'd be not intoxicated. So we would say, I believe if we look at, well, let's just look at all of them. Denotes the probability of screening driver and finding that he or she is intoxicated. That's P of W. So that one's out. P of W complement denotes the probability of a driver passing through the sobriety checkpoint. Literally every driver is going to pass through the checkpoint, and then the ones who are intoxicated will get pulled to the side, and the ones that aren't will just keep going. So this isn't it. Denotes the probability of a driver being intoxicated. That is also P of W. Well, this is not quite P of W. So this is they're intoxicated, but not necessarily they get caught for it. But still, it's not what we're looking for. So it's got to be D, and let's just make sure that it sounds right. Denotes the probability of screening a driver and finding that he or she is not intoxicated. Now, what does it equal? Well, again, P of W complement should equal 1 minus probability of intoxicated, 1 minus 0.00454, because that was what was given as PW. This equals and this is where you have to be a little careful. In some of these problems, they want you to keep every single decimal. And in this one, they do. So you get kind of a lot of numbers here. But it's basically 99% chance that you're not going to catch someone, or they're not going to be intoxicated. Good there? Hopefully those are the easy ones. Just subtracting numbers from 1, basically. The next one's a little more interesting. And now we'll start to get into some of the more challenging stuff. So it says, use the data in the following table which lists drive-through order accuracy at popular fast food chains. Assume that orders are randomly selected from those included in the table. So basically you have 4 different restaurants labeled A, B, C, and D. And then at each of those restaurants, your order can fall into 2 categories. It was accurate or it was not accurate. Now, since we would typically like to use the letter A for accurate, but since A has already been reserved for this restaurant, let's use AC for accurate. And then we'll use AC complement for not accurate. just to save us some writing. Okay, now it asks, if one order is selected, find the probability of getting an order from restaurant A or an order that is accurate. So we want A or accurate. A or accurate. The way you would write this in probability is this. Or is the union symbol. So this would be the probability of getting an order from restaurant A or getting an accurate order. This is equal to the probability of getting an order from restaurant A plus getting an order from any restaurant that's accurate. So let's start with that. The probability of getting an order from restaurant A. Oops, I forgot the most important step. Okay, this first thing I'm going to show you here is something I want you to do on every single table problem. When you see a table problem, I don't want you to think about anything other than this first step. And that is you're going to immediately add up all the numbers. So you're going to immediately add an extra column. That's a total column. And you're immediately going to add another row. That's a total row. And you're going to do this anytime you see a table like this. It'll be the first thing you do, and you shouldn't have to even think about it. So this total here is totaling up all of these numbers from left to right. So you're going to add 313 and 262 and 250 and 150, and in this problem you'll get 975. And what this means is there were 975 total accurate orders. Then you're going to add up the 33, the 53, left to right, all these bottom numbers, and get 137, which is the total number of inaccurate orders. Then you're going to add down each of these columns, and you're going to get 346, which is the total number of orders from restaurant A, 315, which is the total number of orders from restaurant B, 287, 164. And now you can either add these four numbers left to right or these two numbers top to bottom, and you'll get what's considered the grand total, which is all of the orders that were made. And in this problem, it's 1112. And once we've done that, now we can start looking at probabilities. So the probability of restaurant A is the total number from A, 346, divided by the grand total, 1112. So this is just asking, well, what's the probability that I went to restaurant A? Well, it's just the total orders from A divided by the total number of orders. How about for accurate? So the probability of getting an accurate order is the total accurate row, 975, divided by 1112. Does everyone see how I got those numbers? So total accurate over grand total, total from A over grand total. Now there is a mistake here. It's not a mistake, but there's one more thing we have to consider. Notice that this 313, which is the intersection of accurate and A, didn't we count that twice? We counted it in this number, yes. And we counted it in this number, yes. That's a problem. So we just counted this number twice, and so we have to account for that. And so we subtract the intersection of A and accurate. So we counted it twice, so let's subtract one copy of it, and then we'll be okay. So we're going to subtract. This symbol here is intersection. Did I teach these symbols, U and upside down U? I haven't taught those yet? I never showed you those? Okay, then we need to show you those. Okay. This is called the union symbol. And it means if I have two sets, let's use this example right here. A and accurate, the union symbol says take all of the accurate, take all of A and take all of accurate. So you take all of these numbers. And the word or is a giveaway for that. This symbol here is called intersection. And the word and is a giveaway for this. The intersection is merely the overlap of your two events. So the intersection is just this little sliver here. And you can also see this graphically. So in the union, notice when I shaded in all of A, and then I shaded in all of AC, this overlap got shaded twice, right? So that's also graphically how you can prove that you need this part here. Okay, so this intersection is the place where I overlap A and accurate, which is this number right here, 313. So let's subtract 313 over 1112. Notice you use 1112 as the bottom for all these numbers. And if you do this, you will get, they have a common denominator, so you can just add these top numbers together and subtract this one. You'll get 1008 over 1112, which is 0.90647. Rounded to 3 decimals, we'll call it 0.906. So there's about a 90% chance that you will get either an accurate order or you got it from restaurant A. Are the events of selecting an order from restaurant A and selecting an accurate order disjoint? Disjoint events means no overlap. And in Venn diagram form, it would look like this. Here's my restaurant A. Here's my accurate orders. There is no overlap between them. Well, let's just think about that logically. If there's no overlap between these two, can I ever get an accurate order from restaurant A? No, exactly right. So this would mean you can never get accurate order from A. But we can prove that wrong, right? How? There were 313 accurate orders from A. So if this said 0, then maybe this would be true. But even then, it's probably not. So this would be, are they disjoint events? We would say the events are not disjoint because it is possible to get an accurate order from restaurant A. Any confusions there? This is where they get to be a little more complicated, right? Well, we've got quite a few examples on these, so hopefully it'll start to really sink in. Okay, 15. What would be step 1 when you see a table like that? Totals, good. So let's immediately add a total column. And then let's immediately add a total row. This is again accurate orders versus inaccurate orders at different restaurants. And now if you add up these numbers, you'll get 356 total from A, 320 total from B, 282, 132, 950 total accurate orders, 140 not accurates, and 1,090 grand total, or 1,090 total orders. If two orders are selected, find the probability that they're both accurate. Completes parts A and B below. Assume that the selections are made with replacement. Are the events independent? This is tricky to explain, but let me give it a shot. Let's imagine that these orders were recorded on paper. So I have 1,090 pieces of paper written down, and I put them in a hat. And what do these papers say? Well, they say A, B, C, or D, and then accurate or not accurate. Does that setup make sense? So I've just written all the records down on paper, cut them up, put them in a big hat. To figure out, to randomly select which one I experienced, I'm going to draw that piece of paper from the hat and read what it says. So I reach in, I draw it, it says, oh, you ate at restaurant B and your order was inaccurate. Okay. Then I draw again and it says, this time you ate from restaurant D and your order was accurate. Okay. Now, if I reach in and pull out a piece of paper, I look at it and then I put it back in, and then I go to reach in again, the second time I reach in is exactly the same as the first. Does this make sense? Because I replaced that paper and I swirled it around. So now when I go in and reach in again, it's just like I've reached in for the first time. It's no different. That is what we call events being independent. Because I replaced that piece of paper. So it's like I just restarted the experiment all over again. Where this breaks down is if I pull out the paper and then set it aside. Why does it make it a difference? Because now I go from 1,090 pieces of paper in the hat to 1,089. And then I pull out another one. Now I have 1,088. Then I pull out another one. Now I have 1,087. And that's, if you remember in the last probability, we used this number as the denominator. But if that's changing, then my probabilities are changing. But for independent events, when I use replacement, this number will stay the same. So they want us to know the probability that both of my orders are accurate. So I take two orders. So basically I want the probability that the first one is accurate and the second one is accurate. So let's use 1 and 2 here. Well, if these are independent, which we just argued they are, then that's just the probability that the first order is accurate times the probability that the second order is accurate. So let me formalize this actually. So what I'm using is this. For independent events, the probability of getting A and B is just equal to the probability of A times the probability of B. You just multiply them together. Now this only works for independent events. So the probability that the first one is accurate is just the total accurate orders, 950, divided by that 1090 total. That's my first order being accurate. But now if I put the papers back in, my second order being accurate is the exact same. It's 950 over 1090. So it does not change the probability. And if you multiply these two numbers together, you'll get 0.7596. To 3 decimals, we'll call it 0.760. And we'd say the events are independent. Okay, now for the second part it says without replacement. So in this one, that's the case where I read the paper, see what it says, and I set it down on the table. I don't put it back in the hat. So what you get is for without replacement, the probability looks like this. The probability of A and B is equal to the probability of A times the probability of B given that A occurred. So in this one, because we didn't replace the first information, I know that my first drawing was an A. So in this problem, it'd be the probability that my first order is accurate, and the probability that my probability my second order is accurate is equal to the probability that the first order is accurate times the probability that my second order is accurate given the first was accurate. Now, the equation looks complicated, but the logic, I hope, is pretty simple. The probability that the first order is accurate is 950 over 1090. Now, what's the probability that my second order is accurate given that I took that paper and put it down? Let's start with the bottom. How many papers are in the hat now? 1089. So this number goes down by 1. If I know that the first drawing I made was accurate, how many accurate papers are left in the hat? 949. That's the key. So that number changes. Both numbers change. But that's all there is to it. You're going to take this number times this number, and you get a slightly different number. It's 0.7595. So notice the difference here. 96 for this one, 95 for this one. So it's just a slightly bit lower. Now, unfortunately, they round to the same number. So when you round to 3, you get 0.760 still. But the key is these two numbers are different. And because these two numbers are different, we would say this event here are not independent. Might be one of the most important problems in this section because it tests this idea of independence and replacement and without replacement. And you have to really logic your way through this. It's not something that is necessarily just follow the equation. You have to think your way through it. Okay, 16. The challenge in 16 is they want us to build the table ourselves. So in the previous two, they gave us the table, but now we have to build it ourselves. So it says, use the following results from a test of marijuana use, which is provided by a certain drug testing company. Among 143 subjects with positive test results, there are 26 false positive results among 153 negative results. There are 3 false negatives. Complete. It says, hint, construct a table. So we're looking at marijuana use, so let's use M for that. And we're looking at a drug test where you can either be positive or negative. So let's use P for positive. So our table would have 4 squares in it. The person used marijuana, the person did not use marijuana. The person had a positive drug test, the person had a negative drug test, which we'll use as P bar. So these are the 4 categories we can have. But again, let's say I gave you this table. Step 1 would be, let's make a total row and column. So you would still make your total column and your total row. And this is where it gets a little tricky because now we have to fill it in. So the first bit of information says 143 subjects with positive test results. So notice this 143 is the total P. It's the total positive test results. So this row here, the total is 143. I'm going to skip this piece of information for right now. This one says 153 negative results. So the total for P bar, which is negative, is 153. Now notice that immediately allows us to find the grand total, which would be 296. So we know we had 296 subjects for this test. Now let's try to figure out these other two bits of information. There are 26 false positives. So a false positive would be someone who tested positive, but they do not use. You see how I'm going to place this number? So these 26 people are in the positive row, but they're false positives, which means they did not use it. So they're in M bar. So 26 would go here. Now notice that allows us to solve for how many people tested positive and did use marijuana. All you have to do is take 143 minus 26, and you'll find there are 117 people who did use it and they tested positive for it. Okay, now the second bit of info is there are 3 false negatives. A false negative means you tested negative for the drug, but you did use it. So this 3 goes right here. And then this square would be 153, the total, minus this 3 here, or 150 people didn't use the drug and they tested negative for it. And then we can add straight down and get 120 for total users and 176 for total people who did not use. And again, these two numbers should add up to 296, and they do. So everything checks out. So that's the hard part. That's the table. And now we can answer any question about it. So the first question is, how many subjects were included in the study? Well, this grand total here is the same as n, the sample size. So that is how many people were in the study, 296. How many subjects did not use marijuana? So they're asking for the number of people in M complement. It's just the total in M complement, 176. What is the probability that a randomly selected subject did not use marijuana? So that's, notice the difference here. This is the number in M complement. Now they're asking for the probability of M complement. Well, that's just the number in M complement divided by the total, or it's the two numbers we just found, 176 over 296, which turns out to be 0.5946. Rounded to 3 decimals, we'll call it 595. Anything you'd like me to go over there? Okay. Once you have the table, then it becomes pretty easy. All right, 17. Among 9,841 cases of heart pacemaker malfunctions, 428 were found to be caused by firmware, which is software programmed into the device. If the firmware is tested in 3 different pacemakers randomly, selected from this batch of 9841, and the entire batch is accepted, if there are no failures, what is the probability that the firmware in the entire batch will be accepted? Is the procedure likely to result in an entire batch being accepted? So let's use M for malfunction. So we want the probability of a malfunction. Well, it would be the 428 defective that they saw divided by the 9,841 pacemakers. And this is 0.0435. So it's only about a 4% chance that you're going to get a defective pacemaker. We're also going to need the probability of the not malfunctioning, which is just 1 minus this probability we just found, which is 0.9. Let's see here. I'm changing these numbers a little bit to make it easier for us. What should be 0.956. Well, 0.9565. Fine, let's just do it. Carry the digits that we need. Okay, so 4% chance it fails, 96% chance it does not fail. Now we want, for this thing to pass, we have to have 3 non-failures. So the probability of our batch passing is equal to the probability of 3 no malfunctions, which is equal to the probability that the first one doesn't malfunction, and the second one doesn't malfunction, and the third one doesn't malfunction. Well, in a sample this large, we're going to assume that these events are independent, that the first one malfunctioning does not affect the second one malfunctioning. Does that make sense? And actually, I don't even need a big sample size for that. One pacemaker failing or breaking does not make the other one break or fail. So this would just be equal to the first one doesn't malfunction times the second one doesn't malfunction times the third one doesn't malfunction. And these probabilities do not change, so they're all 0.9565. So it's 0.9565, 0.9565, 0.9565, and there is an easier way to do this. What would it be? 0.9565 to the third power. Make your life easier. That way you only have to type that decimal number once. Raise it to the third, and what you'll get is the probability is 0.8751. Rounded to 3 decimal places, 875. So there's an 87.5% chance that the procedure will pass. So this is plenty high enough to be that, say that it's likely to result in an entire batch being accepted. Good there? Okay. The next one is tricky. But it's the last one where we have to do math. The last 2 are just vocab word ones. So let's kind of take our time on this one and make sure we get it right. Okay, so refer to the figure below in which surge protectors P and Q are used to protect an expensive high-def television. If there is a surge in the voltage, the surge protector reduces it to a safe level. Assuming that each surge protector has a 0.97 probability of working correctly when a voltage surge occurs, complete parts 8. So we're going to call this probability of working correctly W. So the probability that this thing works is 0.97. Now let's immediately, and I encourage you to do this on a test for partial credit at least, let's immediately write the probability that it doesn't work. Well, it's just 1 minus that number, or 3%, 0.03. So there's a 3% chance that the thing doesn't work, there's a 97% chance that it will. If the two surge protectors are arranged in series, so series picture is here, what is the probability that a voltage surge will not damage the television? Well, notice that if either of these work, it's going to stop the surge, right? So as long as P works, I don't care if Q fails, it's going to stop the surge. As long as Q works, I don't care if P fails, it's going to stop the surge. So this is the probability of, the probability that this thing will damage would be the first one fails, P fails, and Q fails, which would be the probability of WP times the probability of WQ. Again, we're assuming independence. We're assuming that the likelihood that Q fails does not depend on the likelihood of P failing. They're independent devices. So we just have to take 0.03 times 0.03, and we will get 0.0009. Now, let's be a little careful with what I'm saying here. What we just calculated was P fails and Q fails, which means my TV is broken. It just got wrecked. We wanted the probability that it does not get damaged. So the actual answer is 1 minus that. So the probability of no damage, where do I want to write this? Probability of no damage is 1 minus 0.0009, which is 0.9991. So in series, there's a 99.91% chance that your TV is going to be just fine. Okay, in the second one, we have a parallel configuration. Now in this one, for it not to damage my TV, notice I need both of them to work. Because if P fails, the surge is going to come across both lines here. If P fails, it gets to my TV and wrecks it. Or if P is working fine, but Q fails, it's going to go across this line and wreck my TV. So this is a bad idea, because if either of these fail, my TV is going to get wrecked. So a simpler way to do this one is just to say, well, for it to not get damaged, I have to have P work and Q work. So this would be the probability that P works and the probability of Q working. Again, they're independent. So this is just the probability of P working times the probability of Q working. And this would just be the 0.97 times the 0.97. And this one's a lot simpler, 0.9409. So for this one, you just need them both to work. You don't have to do this complement at the end. So we would say 0.9409. Now it's pretty simple to see which arrangement should you use. Clearly the series one is better because that gives you 99.9% protection, where this one only gives you 94%. So the best answer is the third one. The series, so these two parallels are gone. The series arrangement provides better protection because it has a lower probability of protection. No, we want higher probability. So better protection, higher probability of protection. That's the last hard one in this section. Is there any questions on that one? That one can be tricky. You got to really think logically about what has to happen for things to either work or not work. Okay, the last two. I tend to give the last couple as softballs so we can end the class with confidence. So PA plus PA complement is equal to 1. This is a way to express the blank. Well, I said this is called the complement. So we're probably just looking for that word in the answers, right? So this is called the rule of complementary events. A blank is any event combining two or more simple events. So I said things like P of A, P of B, P of accurate. When you just have one thing in here, these are called simple events. Anytime you have more than one thing written in your probability, like probability of A or B, which is the same as probability of A union B, or probability of A and B, which is the same as probability of A intersect B. Or like we just learned today, if I did something like the probability of B given that A occurred, a conditional probability, these are all examples of what we call compound events. So they're combinations of simple events. So the answer here is they're a compound event. And that will conclude section 4.2.